So, welcome back, people. We'll finish this up fairly quickly here. Unfortunately, my understanding of quantum chemistry is somewhat limited, and I got a few equations here that are going to be cropping up that I'm really not sure what they mean or if I'm using right. I'll show them here towards the end of the video, and if somebody can leave a comment that would help me figure out what's going on, I would appreciate it. But in the meantime, let's just finish up our calculations here. We did get converged results, as you recall, on the hydrogen molecule. In fact, they were like instantly converged results, and we left off in the last video just doing some calculations using those results. So let's continue on with that. We can calculate orbital energies here using equation 3,243 in Szabo and Osland, and we're getting now same as we got from solving the secular equation, the same numbers here that are starting to look kind of familiar. So yeah, I came to the conclusion there are so many ways to get the diagonalized Fock matrix. Just plugging in here to the HartreeFockH2 equations here to see if we really did solve them. Does the left-hand side equal the right-hand side? When you solve a set of equations, it is kind of good to take your solution and substitute it back into the equation and see if it satisfies it. So we'll do that here. We'll take our converged values, results that we got, and put them in, and just make sure the left-hand side, F times C, equals the right-hand side, S times C times the array of orbital energies. So yeah, it is. It looks like we did solve the HartreeFockH2 equations. In the basis where we make the overlap matrix diagonal, make it go away, it's did we solve that as well? So we have all those values, so we'll just again pop them in here. Does the left-hand side equal the right-hand side? And yes, they do. So we solve the transformed Rutan equations that kind of look like a vector eigenvalue system. So it's good, just a nice verification. Nice to see these relationships are working for us. A few other identities here that we're supposed to be able to verify, and I think we are here. Just P times S times P equal 2P. Yes, it does. I'm not exactly sure how you'd set forth to prove that. It's not obvious to me anyway that they ought to be equal, but according to Szabo they should be, and according to our calculations they are. So that's about as far as I'm able to take that for now. Verify a few other identities here. U dagger S times U equals our S1 half matrix, or sorry, our orthogonal S matrix. Yes, they are. They do. And that pretty much then brings us to the kind of the end of our calculations. Let's see. So yeah, we come now to the fact that the hydrogen molecule is a symmetrical system. There exist analytical equations for evaluating some of these quantities. So these come from Szabo and Osland, page 163. Some of these I've seen also in the Macquarie textbook. So here we can use these handy analytic equations, fairly simple equations, and we should be able to see some familiar values here show up. So we should be, I believe we are. Equation 323, Szabo and Osland, you actually can use the results here to make calculations for the hydrogen molecule ion, the one electron ionic system. So sure enough, we can do that quite easily. Calculate our orbital energies again using these relationships. Yep, we've seen those before. Those values there for the orbital energies, we've seen those a number of times. Equation 3 927 to calculate the total electronic energy. Sure, we do. If we add our nuclear repulsion piece to it, we get, again, familiar values there. Okay, this brings me to something where I just come up to limitations on my understanding of what I ought to expect here. These are some equations that I found in the little book by Quinn, Computational Quantum Chemistry by Charles Quinn. So let's run through and do those. These are normalization values that come from page 3, table 1 in Quinn. I'm pretty sure those are correct. And then this is a well-known value for calculating the overlap value of the hydrogen molecule, and it seems to also work for the hydrogen molecule ion as a function of nuclear separation. So I call that S12 exact. That is Macquarie textbook equation 913. That's the old edition of the textbook, first edition. So I'll calculate that, get a 0.752943. Also 923 Macquarie, specifically for the hydrogen molecule. I can calculate a exact J value here. Now, should I feel disappointed that these aren't agreeing with the S12 that I had way back up here that I calculated in step 2? Let's go and find that. There it is. I had an S12 value overlap of 0.6593, and that's certainly quite a bit different from what I got down here. And I guess I just don't know, is that to be expected, or is it a different model? I'm not really sure why that has happened. I would have felt better if I'd have gotten that same value here instead of 0.75. Same with the J exact value. That doesn't agree with any J value I calculated up above. Macquarie 919 says I should get an H11 value by -1 plus J. That gives me a number that I haven't seen before. It certainly doesn't correspond with any H value I've calculated before. And then here's a mysterious equation that I took from chapter 2 of Quinn. I really don't know where he got it or how he got it. I just found it in there, kind of squeezed it out, and it's a numerical approximation to get the overlap integral for the hydrogen molecule. So I did that. I did a numerical integration of it with the two normalization values in front, and it gives me a nice value and good agreement here with the exact. I mean, there it is, 6 decimal places, 752,943, 752,943. So that was kind of nice, but it certainly doesn't agree with my S12 that I was using up above. Also kind of rooted out of Quinn. The equations aren't exactly in there, but I could kind of back them out and get these equations, and I'm not sure are these supposed to or not supposed to agree with some V or T integrals that I had up above. I don't really know. I guess I really don't understand what I'm calculating here in its relationship to the self-consistent field calculations I've done. So if anybody can help me with that, I'd be very appreciative. It'll certainly help me understand this a little better. But yeah, those values are certainly not in agreement with values from up here. At least not obvious, not that I can see. But I think we did do the SCF calculation for the hydrogen molecule correct, and I think these values here are correct. It's just relating the two is kind of beyond my understanding of nuclear chemistry at this point, but I'll leave that for you. If anybody can figure it out, I'll be really, really thankful. I hope this video helps folks, and thank you for listening.